As the sir told in their lecture, Geol 2100 plus 200 kV. Basically, when we are talking about TM, then we say accelerating voltage. Reference is accelerating voltage. 80 kV. Sometimes coming 80 kV. Their voltage is not exactly 80, 120 kV. In that 80, 100 and 120 kV is there. That is needed for biological sample. One time that is normal time. We have also that not working right now, but that was up to 120. Then advanced next version comes to 200 kV. Means kV means kilovolt accelerating voltage it is generating from top. Smaller wavelength it is generating is higher accelerating voltage means smaller wavelength, finer resolution. And again, as I told, cost is going to add. After 200 kV and again filament, we are talking about filament. Just like we have purchased electric bulb, simple bulb, tungsten 12 rupees, 50 rupees. CFL or other type of fluorescent bulb that cost in hundreds. So same tungsten bulb filament is there, its cost is around maybe 1 crore of time, 120 kV. When we say this have LABC, lanthanum hexaboride filament, it cost is around 4 crore, 200 kV. If we same system we go for 200 kV field emission, just like we have field emission SEM, same field emission TAM will also come. Field emission TAM we go to 100 kV at field emission it cost maybe 15 crore. Like that, completely will vary. 200 kV, then we can go to 300 kV field emission. Again, we are talking of that wavelength. Wavelength going in suppose 5 picometer to 1 picometer. Coming from 5 to 1 picometer of angstrom, 5 angstrom to 1 angstrom, that cost and the resolution, quality, everything is going to change drastically. We cannot imagine. Again, sample quality of as per quality of sample. So this is the overview of things, but the rest machine in all case is same. Fundamental principle is same, everything is same. Layout wise, many times you find some bigger. If it is 300 kV field emission or 200 kV, it's something bigger diameter because it needs some more isolation from external environment. It don't need much vibrations because when we are going to do high resolution image, that thing is going to, I can say, dislocate, disresonate. Because when we tap strongly or movement or outside more or movement, it's going to disturb. In case of high resolution image. So due to that things going to you can say broad in case of 300 kV or bigger TM. Layout wise at the top we have electron gun. Basically it is a reverse of light microscopy. If you talk of first you need to understand light microscopy, then the concept of electron microscopy came. If you go in the history, right? At that time resolution was a challenge because they are going to see through visible light. They are not able to see in much depth. So that's why at the time concept of electron source in place of light come, they have done a lot of things. It will take many years, and from 1935 it will take 1982 to get the Nobel Prize in this. Things have taken the time. Right now keep on moving. If you go in 2017, Nobel Prize for the protein structure was given by the cryo-TM. Cryo-TM is again one more category which means for biological sample under stabilized condition. That is separate instrument. So layout wise electron gun is there. As we are going to deal with electrons, so we need condenser lens. But again, condenser lens is also light microscope, but that is just to control the light. Here we need to control the electron beam, so we need electromagnetic lens. Electromagnetic lens arrangement is there, like cooling is there. And this from inside is not big much, it's just like that column. In that vacuum is there, right? Condenser lenses are there, movable condenser aperture. As sir told in diagram that something is to be removed by putting some strip like thing. It is like some diameter. Light is passing through diameter. Suppose beam is coming like this, so it's passing through narrow diameter. Extra will come as stray, loss in the form of heat. Only a fine beam will pass. Right? This is the purpose of this aperture, and you can see we have different diameter of aperture. As sir showed in one presentation, 10 micrometer diameter, something like they have shown. So there are different diameters. Suppose 20 micrometer, 10, 5, 2, like that. Smaller the diameter, smaller the beam we can generate. Right? So beam just like coming like this, it becomes smaller. But
it's more for the contrast.
Or you can say suppose you have very strong sample, some material science sample, some semiconductor. So you need more penetration to elaborate. But again, if you have some biological sample, so we need not to put it stress. So we many times make the broad beam. Not without aperture because that have bulk illumination, so it will burn the sample. So it's a live things we need to do. This is condenser aperture. This is a sample stage. Here we are going to insert the sample. Right now sample is inside the machine, right? So दिखा देते हैं. So just like नहीं ऐसे में निकालना है. अब बाहर ही लेना है. Right now we have moved the sample somewhere. So now I am putting it to the home. That stage is going to home. It was somewhere because we have searched something. Now bring it to 0 position. X, Y, Z, 0, 0, 0. Stage is here. Now I am taking it out. Here you can see this is an outline. You can see if specimen chamber is ready. This is specimen chamber. I am taking the sample holder out. I need to push it as it is in vacuum. So, and I have make it pump to air. As suddenly you can see it was from ready to not ready. In that part, things get. Rahul ji, sir, please come.